So exercise 1.2, last question of our exercise is, so there is a circular path around a sport field. So suppose it is our sport field. So it is circular path, and Sonia takes the 18 minutes to drive a one round of the field. Suppose that is our starting point. So if Sonia take the one round, so she take the how many minutes? 18 minutes. Next, while Ravi takes a 12 minute for the same. When Ravi is also start to run and they complete in how many? So they take 12 minutes only. So it means what? It means clearly that Ravi take a short time and Sonia take a more time compared to the Ravi. So now they are asking, suppose they both start at the same point and the same time. Suppose both are here and they are start to run. So Ravi, they are completing the one round in just 12 minutes while Sonia taking the 18 minutes. So while both are starting to run, so they are asking what? And go in the same direction after how many minutes? Now they are asking after how many minutes they will meet again at the starting point. So both are running, and after how many minutes they will meet again at the same starting point. So it will be very easy example. So we can take like that, Sonia takes 18 minutes and Ravi takes 12 minutes. So it means what? Here just a time difference, and they are asking how many minutes they will meet again at the same starting point. So for that we will find the LCM. If we find the LCM, we can clearly say that after how many minutes they will meet again at the same starting point. So we can take the factor of 18. So what is the factor of 18? 2. So it will be 9. Now 3 and 3 ones are 3. So and we can also take the factor of 12. So 6, here 2, and it will be 3. So what is the factor of 18? So factor of 18 is 2 into 3 into 3, and factor of 12 is 2 into 2 into 3. So now we want to take the LCM of 18 and 12. So how can we take the LCM? So we can write here which is a common pair. First of all 2 and 3. So we can write 2 and 3. Then which is uncommon? So it will be 3 and 2. So 2 3s are 6. Once again 2 3s are 6. So 6 into 6, it will be how many minutes? 36 minutes. So we can write that after 36 minutes they will meet again at the same starting point. So that is our answer, 36 minutes. You can mention in your notebook. So now we are starting our next topic, that will be the revisiting irrational number. So in that topic we have one most important theorem, it is 1.3. So exercise 1.3 is totally depend on that theorem. We have only just 4 example from the exercise 1.3, but all are dependent on that theorem. So first of all we are starting from that. What is irrational number? We can already discuss that irrational numbers are those number which is not in a form of P upon Q. It means what? They are not in a form of P by Q. And we can take also the example like that, root 2, root 3, root 5 like that. Also we can write like that 1.2, 3, 1 like 0. So it will be continuous. So these all number are called which number? Irrational number. Irrational means we cannot convert that number into the P upon Q form. Clear? So it is called irrational number. And rational means what? exactly opposite to the irrational. It is in a form of P by Q. Here I am taking the two example, and we have in the one question, root 4 and root 9 are a irrational number or a rational number. So root 4 means what? If we take the square root of 4, it means it will be 2, and if we take the square root of 9, it will be 3. So it means what? We can write like that, because if we write in a denominator as a 1, so term will be remain same, answer will be 2, and here answer will be 3. Answer does not change. But what happen if we take the square root? We can convert that number into the P by Q form. So this is not a irrational number. It is which number? Rational number. It is rational number, because we can convert that number into the P by Q form. So from these two, we can clearly suggest that if we take the square root of any term, so we can convert that number into the rational form. And if we cannot take the square root like root 2, root 3, root 5, so it means what? It is in a which kind of the number? Irrational number, because we cannot convert that number into the irrational form. But now if you want to find out the value of that, so you can take the scientific calci, or in your mobile, if you find the value of root 2, so it will be in the 1.373 like that, so 1.41 like that. So it will be in the continuous digit, it will be not AND. So it means what? It is a irrational number. Okay. So we can already conclude that the theorem 1.3, so we can also use that theorem in our exercise 1.3. So question number 1 from exercise 1.3 is that prove that root 5 is an irrational number. So we can already define the term irrational. So the number which is in a not a form of P upon Q, it is called irrational number. So let's start. How can we conclude that root 5 is irrational? By using theorem number 1.3. So for that we have one procedure. So by using that procedure, we can also prove that root 5, root 2 or root 3 is an irrational number. We already know that these three are the irrational number, because we cannot take its square root. But how can we prove that number it is irrational? By using theorem number 1.3. So we have one procedure. So the step 1, it will be, let assume the contract that the root 5 is an irrational number. So first of all, we can start with false assumption. So it will be the rational number. We can start with it the rational number. So if it is a rational number, so we can write in a P by Q or A upon B form. Clear? So if it is in a upon B form, so let assume that here A and B have the common factor other than the 1, and then we can divide by the common factor and assume that A and B are a co-prime number. So we already know that rational number we can write P upon Q form. So here we can just change that parameter A upon B. That will be the little change. And second thing is what? Now that B is in the division term. If it is going into the second side, so it will be in the multiplication. So we can write like that, B root 5 is equal to A. B root 5 is equal to A. Now we can squaring both sides. So if we squaring that term, so B root 5 all square is equal to A all square. So now what happened? B square and root 5 square, it will be only 5. Now we can rearranging that term. So we can write like that, 5B square is equal to A square. And we can conclude that it is our result number 1. Now the second step. So second step is what? Our theorem number 1.3 statement. It is clearly say that what? If A square is divided by 5, so it is A is also divided with 5. So according to our that theorem, if A square is divided with 5, A is also divisible with 5. Now if it is divided with 5, so we can also write like that, A is equal to 5C. Clear? We can also write like that, A is equal to 5C. Now we will put that value in our equation number 1. So here A square is replaced with 5C. A square is replaced with 5C. So here A square, So it means what? We can also write like that 5c all square. Now we can squaring. So 5 square it will be the 25 and c means it will be the c square. So now that 5 is going on to the second side, so it will be in the division term. So we can conclude that b square is equal to 5c square. So again we can see that what here 5 is on with the c. It means what? That means what? B square is also divisible with 5. So it means what? B is also divisible with 5 according to our theorem number 1.3. So therefore we are concluding that A and B having the at least 5 as its common factor. Here which term has the common? C. Here we have 5. Here we have 5. And second, here once again we have 5. So it means what? A and B are at least 5 as its common factor. So this contracts that the A and B are the co-prime number. So this contradiction arises because of our incorrect assumption. So it means what? Root 5 is not a rational number. So so we can conclude that root 5 is an irrational. Exercise 1.3 question number 2. So the question is the prove that 3 plus root 2 root 5 is an irrational number. So we can same theorem we can apply in all the exercise. So how can we start? So we can start. First of all, we can assume the false assumption that let take 3 plus root 2 5 is a rational number. So if it is rational, so we can also write like that is equal to A upon B. Now that 3 is going second side, so we can write like that A upon B minus 3. So that 2 is also going second side, so we can write like that 1 by 2 A upon B minus 3. So we can clearly see that what? This is a rational number. Clear? Because if we simplify that, so we can write like that A upon 3B upon 2B, because we can take B as our LCM. So B is multiplied with 3, so we can write A minus 3B, and B is in a denominator term and it is multiplied with 2, so we can write like that A minus 3B upon 2B. So if we put the value of A and B, so we can convert that number into the rational form. So it means what? 1 by A minus 3B upon 2B is a rational number. So we can also write root 5 is rational number. But we already know that root 5 is not a rational number. So this contract arises because of our false assumption. So we can write, but this contradiction arises because of our false assumption. So we can conclude root 5 is irrational number. Root 5 is a irrational number. So if root 5 is a irrational number, so it means what? These all number are a irrational number. So we can write last statement of this sum is, so 3 plus root 2 5 is also irrational number. Once again we can repeat that sum. First of all, we can start with the false assumption. So this will be, if it is rational, so we can write in a upon B form. and then we can simplify it. If this term is going second side, so it become minus, and then we can take 2 that will be going into the second side, so it will be the denominator. We can simplify and finally we can reach that step. So after reaching that step, we can clearly see that where it will be in the rational form. So if it is in the rational form, we can also say that what root 5 is also rational number. But this we can already know that root 5 is a irrational number. So this is arise because of our false assumption. So we can write like that, root 5 is a irrational number, and if root 5 is a irrational number, so this all term will be the irrational number. So we have the 2 more sum which is given in your exercise. It is the same sum like that, 2 plus 5 root 7. So we can also, we have the number of sum like that. Sometimes they are giving the plus, or sometimes they are giving also the minus sign. So we are using the same procedure. Clear? The procedure step will be remain same, but the number will be changed. Now we are going to start our next term. It will be the question 3. Question 3 first, prove that the following are the irrationals. So we can use the same procedure step. So for that we can start like that, let take 1 upon root 2 is rational number. So if it is a rational number, so we can also write like that, it will be a upon b form. Now we can cross multiply, so b multiply with, so we can also write like that, b is equal to root 2a. Now if b is equal to root 2a, and we can also write like that, b upon a is equal to root 2, because that term is going on to the second side. Here we can see that what, it is a rational number because it is in a p upon q form. So if it is a rational number, so we can write like that, here b upon a is a rational number. So root 2 is also rational number. But here we know that root 2 is not a rational number, it is an irrational number. So it is arisen because of what? Our false assumption. So we can write like that. So same step, but the number will be changed. So but this contradiction arisen because of our false assumption. So root 2 is irrational number. So finally we can conclude that 1 upon root 2 is also irrational number. So this is our question 3. First we can prove that 1 upon root 2 is also a irrational number. So from question 3, second, prove that the following are the irrational. Second, it will be the 7 root 5. We prove that these number are the irrational number. So we can start like that. Let assume 7 root 5 is a rational number. So if it is a rational number, we can write like that, 7 root 5 is equal to a upon b. Now this 7 is going second side, so we can write like that, a upon 7b. So it will be in the same like the rational number form, because a upon 7b, it is a one kind of the rational number form. So here we can write a upon 7b is a rational number. So fact that root 5 is also rational number, but we know that root 5 is not a rational number. So because this is arisen because of what? our false assumption. So we can write root 5 is a irrational number because of our false assumption. So finally we can write 7 root 5 is irrational number. So it means what? From this all sum we have one thing that will be the common. Here I am writing that so you can just have an idea. So from this all sum we have one common thing is what? If irrational number is multiplied with any of the rational number, so it will be the answer is always irrational. And here once again, if one it is in the rational and one it is in the irrational number. So if it is multiplied with the rational, so answer will be the irrational. So if we subtract from any of number of, if we add this number to the any of rational number, so answer is always irrational number. And same thing will be happen in the last two example also, because here we see that what? Root 5 is an irrational number. If irrational number is multiplied with the rational number, answer is always irrational number. Same thing will be here. Same thing will be here. If root 2 is an irrational number and if it is divided with 1, so answer is also irrational number. So now the last term of that exercise, prove that following are the irrational number. So it will be same as our question number 2. So it will be in your homework. So just note down that all sum in your one fair book. So we can conclude that this exercise will be the depend on our theorem number 1.3. So next and the final topic of that chapter, it is revisiting the rational number and their decimal expansion. So we can already know that how can we convert fraction into decimal or decimal into the fraction. So for that I am taking the one of the example. So from that you can conclude that how can we convert that decimal into the fraction, or fraction is also known as in the rational number form. So for that here we can take the sum of the example. So you can get the idea how can we convert decimal into the rational or a fraction form. So for that here we are taking 0.375. So after point we have how many digits? 3 digits. So we can also write like that 375 upon how many digits? 1, 2, 3. So 30,000. So it will be in the which form? P upon Q form. So it is a rational number. So it means what? If the any of the number that will be the terminate means what? It will be ended. So we can convert that number into the rational number form. So here we are taking also one of two more example. Here after point we have how many digits? 4. So we can write 10,000. And here after point once again we can write 10,000. So now I am taking the fraction of 1000. So what is its fraction? So we can also write like that. 1000 means 10 raised to 3, because 1000 means 10 raised to 3. 10 raised to 3. Now once again we can take 10 means what? Factor of 10, it will be 2 into 5 all raised to 3, because 10 is equal to 5 2s are. So 10 is also replaced with 2 into 5 or 5 into 2. So from that sum we can conclude that if any number in the denominator term, here see that in the denominator term, the factor, if denominator having the factor of 2 and 5, so we can convert that number into the decimal form. But if we do not have in the denominator 2 or a 5 or any other number like 3, 4 or 7 like that, so we cannot convert that number into the decimal form. So here we have must include that term is what? If denominator having the factor of 2 and 5 only, so then and then we can convert that number into the decimal form. Otherwise we cannot convert that number into the decimal form. We can take the we can also see the sum of that example in our theorem number 1.5. But before that, we can also here 10,000, so we can also write like that 875 into 10 raised to 4. So once again 875 upon 2 into 5 all raised to 4. So once again the factor of 10, it will be 2 and 5. Here it will be the similar, the factor of 10,000, it will be 10 raised to 4, and then we can also write like that 5 into 2 all all raised to 4. So from them we can conclude that our theorem number 1.5, according to our that theorem, here we can see that what? So in that theorem we can see that let x be the rational number whose decimal expansion terminates, then the x can be expressed in a p upon q form. So this term is important. If any decimal expansion terminates means that, clear? Terminate means what? They can it means remainder will be 0. Terminate it means the remainder will be 0. Then x can be expressed in a form of p by q. So for that we are taking the two examples. So you can get the idea how can we convert that number into the decimal form. So for that theorem we can take the one example 3 upon 8. So the factor of 8 we can write like that 2 raised to 3, because 2 into 2 into 2, so it will be 8. So 8 is replaced with 2 raised to 3. So if I want to convert that number into the decimal form, so here 2 raised to 3, so we are multiplying 3 into 2 raised to 3 into 5 raised to 3 into 5 raised to 3. Here I am multiplying and divide with 5 raised to 3 and 5 raised to 3. Why? Because we want to convert that rational number into the decimal expansion. So here see that 3 into 5 raised to 3, it means 125 upon, here both having the power of 3, so we can also write like that all raised to 3. Now 125 3s are 5 3s are 15, 7 and 3 1s are 3. So it will be 375 upon 10 raised to 3. So now 10 raised to 3 means what? 375 upon 1000. So 1000 means what? 0.375. So it means what? We can convert that fraction into the decimal form only and only if we have the factor of 2 or a 5 in its denominator term. So it is depend on our theorem number 1.5. So similar we have the one more example 13 upon 125. So what is its factor? We can write like that 13 upon 5 raised to 3. Here we have in a denominator we have a 5, and here we have a denominator we have a 2. So here we are multiplying with 5 raised to 3, but in that we have already 5 raised to 3, so it is multiplied with 2 raised to 3 into 2 raised to 3. So 13 into 8 upon 5 into 3 all raised to 3, sorry 5 into 2 all raised to 3. So now so it will be 104 upon 10 raised to 3. So now we can convert that number into the decimal form. Clear? So from that to example, you can just get the idea how can we convert fraction into the decimal. If they have in the denominator, either it will be 2 or 5 or both. Clear? So we can convert that number into the decimal form. So now the next theorem is what? In a next theorem, they are asking that in theorem number 1.6, first of all, we can read that statement so you can just have an idea. Let x is equal to p by q. It means what? It is a one kind of rational number, such that the prime factorization of q means denominator term, is of in a form of 2 raised to n into 5 raised to m. So, and m and n are the negative integers, then x has an the decimal expansion which terminate. So, understand how can we express that theorem in our example. So, for that we are taking one example. So, you have just idea how can we convert that number into the decimal form. So, for that we are taking one example, 1 by 7. So, we are starting like that, 7 divided with 1. So, here we are 10. So, here we have a point, then 7 1s are 7. So, it will be 3. Now, once again we will put 0, 7 4s are 28. So, it will be 2. Once again we will put 0. So, 7 2s are 14. So, here we have a 6. Once again we will put 0. So, 7 8s are 56. So, we have one 4. Now, 7 5s are 35. So, we have a 5. Then 7 7s are 49. So, here once again we have a 1. So, once again we will put 0. So, these all number are repeated now. 0.142857. Once again we have one same 0.142857. So, in class 9 we have the same sum like that. If you know 0.7 raised to bar. So, it means what? We can convert that number into the rational number form. Clear? We can convert that number into the rational number form like that, 777. So, if it is same digit, it's repeated. So, we can convert that number into the rational number form. So, similarly, we can also convert that number into the rational form if we use our theorem number 1.6.